Okay. So let's first write d s gamma. So this is like the density we've been using in the other distributions. Is that okay? All right. So that will be function. This function will take x and what? Theta. Is that okay? That's the only thing we. So we have to go into the. We are going to write what we see over there. Maybe I need to. Okay, and then have this as also. So the density is, but you can also look, if you can't see it, you can look at it on your phone as well, since we, so the density is this, right? Remember it's at the top, but we can look at it over here too. Because that one is pi, the product of fxi. Okay, so what it means is that we need theta squared, right? And then we divide by what? 1 plus theta. Okay, so let's do that. So let's say fx will be equal to, okay, so this theta divided by 1 plus what? Theta. Okay. Theta squared. Okay, yeah. Okay. Then, because I'm going to multiply this by another, I can put all of them in bracket. Is that? Oh, okay. All right. Thank you. So like this. Then I put all of them in what? In bracket. Okay, that's important. Other than that, you may have some, even though you use board mass, you may. Okay, next, we open a bracket, a parenthesis, I should say. And then what do we have? We have 1 plus what? Theta over 2. So that one, I'll put that one in bracket as well. In the parenthesis, theta divided by 2. Okay, then I'll multiply this. Theta divided by 2. I'll multiply that by what? S squared. I want to bring this down so that it makes easier for us to see. Okay, then what next? That is, we multiply it by what? ESP, and it's what? Negative theta times x. Is everybody okay with it? So we are done. Negative theta x. So as a matter of fact, I can even take out the curly bracket and write everything on one line. But it's not. So let's return fx. So this is the density of the gamma distribution, the S gamma distribution. You have to be careful with the parentheses. Yeah, open and then work inside. You open, you work inside. Don't open and delete and then you close it yourself. You make mistakes. So that is ds gamma. We can also write a likelihood, isn't it? Is everybody okay? We can write the likelihood because it's already been given to us. Do you want us to do so, or we should just use the ds gamma too? Let's leave the likelihood as an exercise. Oh, it's the same thing. Once you know, because what we are going to do, we can also use this to do it. So the alternative, we will use that as an exercise. Okay. So I'm going to write like S gamma, which is a likelihood function. What is the likelihood function? It is telling us that this is a likelihood. So we can find a log likelihood. That will be sigma log of this. Is that not the case? That's it. And that is what we have written over here. So it will make life easier for us if we do so. So it's a function that takes in x and theta. And in this case, we'll say x and pi and we are going to do this. So our likelihood, if we find the log of that to get a log likelihood, the product will become what? Summation. Is everybody okay with that? This one. This is likelihood. So usually we use a log likelihood. If we find a log, this will become a summation log of f of x. So that's what we are going to use over there. So we are going to write sum. Then we are going to write log. So instead of product, I can also use the log likelihood, but it's easier, the likelihood, but it's easier to work with all the log likelihood. So we're going to call this dx gamma. So dx gamma, and then x is equal to x, and then theta is equal to what? Pi. Yes. Okay, so you see, we are going to call this in the optim. Remember, in the optim, we have pi, the starting values. So my likelihood should always take in the same name. Yeah. So, all right. So this, we can put it in those quotation marks so that when you call it, it's easier to locate it. Okay. What else can we even... so that's it. So that's a log likelihood function. So let me make comment. This is density of S gamma, density function of S gamma, and then over here we are find it's all the log likelihood, the log likelihood function of S gamma. Is everybody okay with this? Okay. Now, if I want to optimize this, we will need the optim. You see, this one we cannot use the fit this R. Is everybody okay with that? Because that the density function we found in the fit this R, there's no S gamma. That's why we are writing our own function to do so. Okay, so let's see, optim. I think we all know what the optim is, so but you can, I don't have the space to do so. But I'll call it mle dot S gamma or SG will be equal to optim. Then I'll have pi. Let's say I take 1. The Fn will be equal to this function, which is that. And then what else do we need? Method, let's use Brent because it's just one parameter. and then x will be equal to our data. What is x? X is the data that we need. So this should this should find our maximum likelihood for the S gamma. So hello, evening. I'm teaching it, so let me finish. Okay, so. I hope now you understand the maximum likelihood process. Usually you write the likelihood function and then you optimize it on the data you've been given. As of now, we don't have any data we are going to use now. So we will wait. And then we are going to do our moment estimation as well. So here I can write that this is for the maximum likelihood estimation of S gamma. Okay, and then so that's it. And then we are now going to go to 2, which will be moment estimation. The moment estimation will be easy because that one is a function. We just go there and what? And so 2 will be what? Moment. Okay, is the parameter likelihood function. Okay, so but this one a moment estimation of yes. I should go up. All right. Okay. So for the maximum likelihood estimation, we have the density function written. We have the likelihood gamma. What I'm saying is that instead of writing this, we could have also written the log likelihood function through this, right? Do you understand that each of them we should get the same thing? But usually it's easier if you go through this step. This one doesn't. If we are writing the likelihood function, we have to write 2 times the length times log this minus 2n log 1 plus theta plus. It's a long, but we can, break it into the density and also sum them. Okay. So for maximum likelihood, you get your likelihood function, you get the optimization step. And that's what we have done over here, which is the optim. We are here to check whether it will work, but I'm sure it will. So we go to the next, which is the moment estimator. Yes.
For the method,
Yes.
we have different ones. If we are to use the optim function.
Yes.
We have different ones.
Yes. You have the method, you have the mid and so forth. Some are not. The Brent is good for when you have one parameter. That's why I chose it.
Okay, but can we do the same thing as we were doing before, where you keep it like that and it will choose the best fits?
No, it doesn't choose the best. It will only give you the first one, which is the mid. Yeah. But there's another, there's a package called Optim X. For that, you can state all, and then it has so many methods. So calculate all of them, and then you can choose the one with the smallest standard error. Yeah. But there are so many optimization routines. Each of them has its own advantages and disadvantages. So let's do the moment estimator. Yes.
Please, why did you put please, can you make it bigger?
Okay.
And then why did you put the DX gamma quotation?
Okay, so that whenever you see when you want to call a function within another function, when you put quotation marks in a name like this, it makes it available in the whole environment. In other words, I can call it even if I have a function and you have 4, I go in a function and another function, you can still call it. So it's a good practice to name your functions with quotation mark. It's so small. Okay. Because of the is it better? Okay, all right. Okay. Is everybody okay? Are you done? Not yet. You have to type fast.
When are you going to run it? Because you haven't run it.
No, we'll run it later. Okay, you can run it but not the Optim. The Optim, we need data. We haven't generated any data. Yeah, but these ones. And you were getting there.
Just enjoy it.
Okay, so the function, the DS gamma and the likely you can run them. Will work, okay. But the Optim won't work. It will. You are way ahead of us. Okay, so let's see. So now we are going to find the moment estimator. So we are going to call it mom, or somebody is still typing. Is everybody okay? All right, okay. So we are calling it mom S gamma. So you see the way I'm naming the functions, it tells you what it is up to. So mom S gamma. So that's a function, and that we need to go back and check the moment estimator. They said equates to so and so and so with the first order, and the mom estimator of theta as what? This. So we are going to write a function to compute this. Is everybody okay with this? Okay, so if you look at this one, what do you need? Mean. You cannot get a mean and put in a function. What basic? You need the basic is the data. Because S bar, you need the data to calculate S bar. Is everybody okay with it? So we are going to just put here what? Data. Or X. Maybe let me use X so that it goes with what is in there. Is everybody okay? All right. Okay, so then we open our curly bracket and end it. Okay. So to do this, I'm going to break it into two so that it becomes easier. I'm going to do the numerator and the denominator. Then I'll divide the numerator by what? The denominator. Okay. So numerator. You can put all of them together if you are okay with that. Okay. So, first of all, I need S bar. So I can calculate S bar. So I can say that S bar is what? Mean of what? X. Is everybody okay? So it means that within numerator I can just call S bar. So this will be what? Negative of what? S bar minus 1. Then I add it. So if you like to, you can turn it the other way, but it's fine. Plus square root is SQRT. So through this we've seen one more. SQRT is what? Square root. So plus. Then what do we have in the square root? S bar minus 1 all squared. And I've already written S bar minus 1. So I'll come and copy, so that it makes it easier for you to finish. So SQRT squared. So I'm going to bring this one down to make it easier for us to write squared. Plus what? 12 times what? S bar. So that's the numerator. Do you want us to just divide this by 2 S bar and go on? Or we should get our denominator? Okay, let's get the denominator. The denominator is what? 2 times what? S bar. Good. And our expression, if I call it mom, will be what? Numerator divided by what? Denominator. And then I return mom. So that's it. Okay, so we can run this and see whether it works. It works? Are you done? Are you done? Not yet. Okay. Okay, please hurry. The numerator. Oh, it's just S bar.
Minus S.
So you see, all that are in the square root. The S bar minus 1. They are all in the square root. You can't find it. It's just a mean. Please, are you done? Can we move on? Good. Okay. So now we have written functions for the maximum likelihood estimator, also moment estimator. Please run them to make sure that they are working. Okay. If they are working, then good. We can move on. The next thing, 3, is generating data from S gamma. So let's go to the simulation study. What we've been talking about is simulation. So this is an example. So now the authors propose a new distribution. They have 2 methods of estimating the parameter theta, either through the moment or maximum likelihood. They want to check which one is the best method. To do this, you need to you need to talk about simulation. Yes, so let's go through it and see what we mean by this. So I think I mentioned inverse probability transform, right? You remember that we can generate a random samples or random variate from the uniform distribution. That's the concept they are using over here. So f of x is equal to, we were using p, they are saying u, where u is an observation from what? The uniform distribution. But in this case, it will not work. So that's what they are saying. And why is it so? You can go and check the density. This is the density. So when you go home, you can try to invert this. Yes. Do you remember we did this for the exponential? We took the CDF, right? So this is the CDF. So if we said this CDF is equal to P, you have to solve for X. That's not possible. Is everybody okay with it? Mm-hmm. So it means that we cannot go by our usual method of generating from the uniform distribution and then we plug it into a formula and then it gives us data from S gamma. But exponential, we can do so. If you remember, we had x of the p to be equal to -1 over lambda log 1 minus p. So if we generate the p from uniform and we put it in there, we get exponential. We can't do it that way. So that's what we are talking about here. Okay. So that's it. So if you look at this sentence, it says fx is equal to u, where u is an observation from uniform distribution. Cannot be odd, explicitly solve for x. So you can't do so. So, however, we can use the fact that the S gamma distribution is what? A special case of the exponential and what? Gamma. Okay. So we are going to use some method to rather generate observations from the uniform, from the S gamma. So please let's look at this. It says to generate this, so as I said, now you should be in a position to be implementing procedures in R. So let's look at this. He says for us to be able to generate data xi from the S gamma distribution with parameter theta, we can use the following algorithm. So when we have an algorithm, we should be able to implement it. Okay. So first, generate UI from a uniform distribution. I think everybody will be able to do that. Yes. Good. Next, we generate VI from exponential with parameter theta. Then we also generate W from a gamma distribution with parameter 3 and theta. Then we are going to use an if condition. If UI, which is what we generated from here, is less than, do you remember this one? That was the mixing proportion. If it is less than theta over this, we say that x is chosen from the exponential, which is v. Else, s is chosen from what? Gamma. So we generate, it's like you have two separate distributions, gamma and exponential, and you are using the mixing proportion. If you toss, it's like you toss a coin, not a coin in itself, but you choose a random number from 0 and 1. If it's less than your mixing proportion, you choose from exponential. If it's greater than, you choose from gamma. And if you put them together, they become a distribution called S gamma. So we are going to do this algorithm. So first of all, we are generating observation from uniform. We are generating one from as exponential with parameter theta, and then we are going to generate one with what? Gamma with 3 theta. Then we use that condition to choose from one of them. Okay, so let's move on. So how are we going to do this? So first of all, they say we should generate U from what? Uniform. So I'll say that the S gamma algorithm so U will be, how do we generate from a uniform? IUnif. So here, by default, the max minimum is 0, max is 1. So we as well can just put just the sample size. So first of all, we need our sample size. Let's say sample size is 10. Then we need theta. So the theta, I'm going to use capital T. So now we have to choose our theta, and then we go and check whether so let's say our theta is 5, which means we want to generate an exponential 5 with parameter 5, and also a gamma with parameter 3 and 5, so to speak. Okay. So our uniform N. Then what will be V? V is going to be what? RSP. So the exponential N is equal to N. We have to also say N is equal to N. Then rate is equal to what? Theta. Is everybody okay with it? Okay. So I can generate these observations now. If you want to generate it and also you want to see it on the graph at the same time, you put them in parentheses. So let's do so. So these are my observations. Oh, n is not found. I need to write this before. Good. So you see I've gotten 10 observations. Yeah. And these are uniformly distributed within the parameters, within the parameters 0 and what? 1. Good. Then the v, let's do. So this is exponential. So v is also exponential. These are exponential distribution. Because the theta is 5, the exponential values will not be so high because it has a mean of what? 0.2. Okay. Okay, next is W, right? And W is a gamma. So we are going to use our gamma. N is equal to n. Then the shape is equal to what? 3. Is that okay? And then the rate is equal to what? Theta. Okay. So I can now generate the W as well. And W is like this. That's also quite small values. Maybe I should go there and let's keep the rate at 0.5 and see how it looks like. Oh, even point. Uniform. If it is point, well, of course, we will have different values. Okay, yeah, so let's make the theta 0.5 so that at least we get values that are not like the uniform. Yes, so make it 0.5, then you rerun. Yes. Next is that we need to get x or our data. So what we have to do is that we will take the first value and then we check is theta over 1 plus theta. If that value is less than the u is less than that, we choose from v. And so who can help us? It has to be a conditional statement. If else. But the formula. If else, we have function, well, we should be, but I'm not sure if it will be able to take the vector. But let's see. So, criteria, right? Or this one, we'll call it pi, right? It was pi, so let's use pi. You can't use small letter because R knows pi, right? Or pi is a value in R. So pi will be equal to theta divided by what? 1 plus theta. So this value, in this case, is 0.33. So what we are saying is that if u is less than 0.33, what do? You choose from an exponential. If other than that, you choose from where? Gamma. Okay, so I'll try your if else to see if it will work. I doubt, but maybe. If else, so if else test. So we have to put our test there, and then it takes, I think we need to select it. We can use maybe air supply or something to implement it. But let's do it first. So that's the format. The test will be what? U less than pi. Okay, so U less or equal to pi. If that is the case, what do? You simulate from V. Else, you simulate from where? W. Yes. Yes? You want to say? Come and sit here. Or you want to go outside and you want to say what I say? Okay. All right. So okay, take it. Okay, so let's see if this will work. It did. So which is quite easy. It did work. But what we are going to do is to check whether it actually works. So we are going to put U, X into, let's say, a data frame, then we check. Is that okay? So let me see, data.frame. Then we have U, and then V, and then W. So let's do that and check. So the first one, we know that if U is less than, so the first one, okay, so let me see, X is assigned this. So then I'll put X alongside it. And then we see the way it looks like. Okay. So let's see what is happening. If you are done, we can all check through. So this one is U less than 0.3. 0.33. No. So we have to choose our sample from W. So you see X is that. So the first one works. Then this one, is it greater than, is it less than 0.33? No. So we will still choose from where? W. So it's also 2 points, so it's fine. Let's see if we have a smaller one in. This one, let's see. 8. Is this one less than 0.33? Yes. So you see X value is the one from V. And so it works perfectly. So you see we are mimicking how to generate observation from what? A mixture distribution. Please, are you done with this one? So so run yours and let's do the comparison and see whether it's just 10 observations. You choose uniform, you choose V, you choose W, and then pi. Then what we are saying is that X will be, if U is less than pi, we choose V. Other than that, what do? We choose from what? W. Okay. So that's it. And then we put all of them into a data frame to check whether what we did actually works well. So if you are done, we can go and check mine together. And then after that, you can check what you got because we'll get different answers. Okay. So let's go in and check. So the first one, U is 0.53. 0.53, let's see. Is it less than 0.33?
Yes.
No, we are looking at this one. Okay, so I'm putting this one aside because that's where we are going to look at it. Look, so this is the condition we are using. If u is less than 0.33, then x is v. So here, is u less than 0.33?
No.
So x will be equal to what? W. So that's why it's the same. Good. Okay. Then we come to the second one. U is 0.36. Is it less than 0.33? No. So where would we choose x from? W. So it's the same. Okay. So the rest are the same. So let me go down and then we get one that is smaller. So it was only one. That is, which is what? Point number 8. And this is that and so forth. And it's not this one. It should have been 6.12. But because it's less than, we choose from the other side. So this is it. Okay. Can you check your own too and see whether it works? Yes. 3 are less than. Okay. And it worked perfect.
Yes.
All of them are greater than. Which is also, that is not really a mixture. Okay. So when we are doing this, the sample size should be large. So we are going to generate observations. We are going to make the sample size large, and then we use a histogram to see the various shapes we will get. Is that okay? So let's do so. So we are all doing the same. So I'm going to change mine to 1000. It means I need a histogram of x. Hist x main is equal to and then so like that. So I think now we don't need the okay. So let me see. I need to. Oh. So this is a distribution from the S gamma. You see, this one doesn't really look like an exponential decay. It goes almost like there is some sort of exponential decay on one side, but it's not typical decay that looks, because it's a mixture. Yes. They are. Oh, yeah, it can do so. Because yes, it ends at a point. And here, and it's because I have increased mine so large, so it's unable to write at the end point. Okay. I'm going to change this to a small number and see how it looks like. Okay. So you see this one, an exponential, the last end should have been up. Should have been the highest frequency. It's not. So it's telling you that there's sort of what? So if we use exponential alone to fit this, you realize that the curve will go up. It won't come down. But later on, when we use S gamma, the S gamma will follow this than the exponential. And we can also use the gamma to do so. Okay. Let's try again. I hope you are also you are noticing how your own works. Okay. So that's it. And then I can go and change this to even point if I want it to take larger values. Let's say like claims. Okay. And we can change theta to a particular value that's small. So let's say I use 2, which means the mean will be 0.5. There it is. There it is. So it's like when the theta is small, it actually chooses more observation from the exponential. If you look at what we've been doing, this one I've changed mine to 2. So you see that all the graphs I'm getting, they actually represent more of an exponential decay. If I change this to 0.02, right, you'll see that the shape will change. Do you get what is happening? So when the mean is large, you tend to also get more observations from what? The S gamma distribution. So that's what is happening. Okay. Do I have this data in the book? Oh, in the journal? I'm not so sure. It's just remission time of 20 patients. It would have been good to replicate what they have done. Application in this. Okay, so we can take any data at all and check. But for now, we are going to estimate parameters from what we have done to see whether our estimators actually work, what we've written. Okay. So here we know the parameter. So let's go and change this one to, let's say, 50 observations. So the parameter is 0.02. That's what I'm looking for. So X is the data we are dealing with. Is everybody okay? Okay. So let's call the mom estimator. Let's call the mom estimator. So compute the estimate. So it's mom est. Was that a function? What was our moment? Mom S gamma. Okay. So mom S gamma. So it needs just the data. So we just put in X. And let's see. What was our parameter? No, what is it? 0.02. What are we getting for the moment? You see, it's close. Okay, so I hope we are getting to understand the concept we are. You got 0. We will not get a say. Yeah. Okay.
Sorry, what are we comparing the 0.0?
The parameter, theta. So the theta we use to generate the data is 0.02. That's what we are finding with the moment.
Okay, so
And
I have 2.
you had 2. Okay, and your value is what?
It's actually negative. Negative 1.69.
You go negative.
Yes.
No, it's assignment.
Yes.
So what is your theta? Run your theta and let's see.
0.02. My theta.
Yes.
My theta, that's the theta.
But your moment estimator is negative.
Yes.
No.
It's possible. 0.2.
Rerun it. Okay, so just highlight this theta and run it. What value do you get? Check it and let's see.
Okay, so 2.
You got 2. Okay, then your moment estimator, check the negatives as well if you have not missed one of them. Because theta is positive. Theta cannot be negative. So check this one. Did you put negative here?
No, please, there's no.
So it has to be 2. One is the assignment, the other is negative. So if you do it just 1, you may run into that problem. So put the numerator assignment negative and then rerun the function again. Do you get what I'm talking about here?
Yeah. It's the same as what.
It's the same.
Yes, the same.
Okay, generate your data again and find the moment. Let's see.
It's also getting
Something may be wrong. Okay, rerun it again. Who has also gotten negative? Put your cursor here, let me see. There. That's fine. Okay, that's fine. But what's your sample size? The sample size is too much. 1,000.
Which one?
No, it's 2. Or is that the same thing? Yeah, you also did the same thing. Delete one of the negative. Yes. It's just 2 times x. And rerun it. Rerun the function. The mom function. Yes. Object X, the small letter. You are using small letter. You change. No, rerun the function. Yes, you have to rerun it. So if you see object not found, then it means X, small letter and the capital letter. Okay, so at least now we know that the moment estimator works, right? Let's check the maximum likelihood. So how do we check the maximum likelihood? We have to go and copy the optim, this one. And then we come down here and say, so this is moment estimator. Then we're going to find maximum likelihood. So you see, we've written all the functions up there. Okay, so obtain, but this x will be equal to x. Is that okay? And then we run this. We have issues. Lower and upper. Oh, Brent needs lower and upper. That's what you had.
Yeah, it's not fair.
Yeah, so you copy lower. The X, let's see, even X, was it small letter? The likelihood X is small letter. Okay, so it's fine. So lower should be equal to 0, and then upper. The problem with maximum likelihood is that we don't know the parameter, but you always have to guess where it is. And in this case, we are guessing an interval in which the parameter is. But this is simulation, so we know the parameter already. As what? 0.02. What I was doing. So I can choose, let's say, 100, just so that they are together. Did I work? Okay, so it worked, but I have warnings. When you have warning, you have to see what the warnings are, because sometimes it can be fatal. So if you type warnings, I will tell you why it is giving you that warning. So warning message. Warnings. Oh, nothing came. Oh, it's warnings. Oh. Okay, I did not get any warning anyway. So let me see whether it worked. So here, it did not. Something is wrong. So it took the upper point. I'm going to use CG to see what CG is. Conjugate gradient. That will not need a upper and lower. Non-finite difference. It did not. Let me use the simulation approach, which is SANN. Yes, which is simulated annealing. I think there's a problem. In log D, nonce produced. Okay, so that may be the problem. But let's see. This one usually works. Yeah. 1.83. So, but we are interested in what? Let me see, theta. Theta is 0.02, so it's not close to it at all. I'll go back and see how. Let me increase it to 500 and see whether I'll come close to it. So it looks like this. Mom is still close. So per 1.34, not too good. Let me check CG. Was the CG and CG? It doesn't work at all. There are several of the methods. The mid will not be good because it's for several variables. Optim. Brent did not work. BFGS CG sun okay, let me go for Brent again and see. Sometimes if I'll change the it's not really doing anything. Oh, I get it. Wait. Remember, okay, so it's a mistake I did. Do you remember when I talk about maximum, like you have to return what? Negative of the likelihood. Because the optim finds the minimum. But we are interested in what? The maximum. So that's the problem. So please go back to your likelihood function. And we are going to return negative of the likelihood. I think I explained. Do we have a marker? No. It's not really, but I think. Okay, so the curve, if you have a curve, please can you look here? You want to find the maximum. That's maximum likelihood. But the routine in R finds minimum. Okay, so the optim finds minimum. So we have our function, and let's say this is what the point when we say maximum likelihood. We want this point. So the value of theta, this is our likelihood function, and this is theta. So theta cap is the value that will give us the highest likelihood. That's what we want. But the routine in R is only programmed to find all minimum point. So how do you get the minimum point? Well, if I negate this curve, it moves, it's like a mirror image, right? Here. So then I find the minimum. It's the same. So if it is here and you turn it this way, this value will still. So that's it. And that's what we did not do. And we are getting answers that are not that good. Okay. So I'll go back and do this and see what will happen, if we'll get any. There are still warnings. I hope it works. I still did not. Optim. I think it's the S gamma, but we wrote it right, so return. Okay, let me put this here to see F, and then like. We did find some log ds gamma theta per x equal to x. And then this one is per like x is equal to. So, okay, let me generate. Let's say I have 2. And I have this. Moment is 1.95. Ah, good. So now it's working. Okay. So let's change our parameter to, let's say, 2. I think it has a problem when theta is very small. So I change theta to be 2. So let's do this and see what happens. Theta is 2. Please, can you, after this, then we can call it a night. The changes. Yeah, 1.75. Yeah, so let's see. The moment is 1.75. MLE is 1.758. Yeah. It gave you error. So let me go back and please, the likelihood, have you done it?
Yes, please.
Okay, so the likelihood should be like this. You have to return negative like that you've done it.
Yes, please.
Okay, good. Then what else? Here, as I change your theta to a number greater than 1. So I did 2 and it seems to work well.
Okay.
I'm going to do 5. If you check the paper, let's look at the theta they use and then we can also work along it. Because usually when I give it out, okay, so theta is 0.1, 0.5, and so forth. Let's see the performance of average bias of MSC. I thought they were comparing maximum likelihood and okay, so yeah, they chose this. I thought they did not compare the moment and the maximum likelihood estimator. But we can do so. And I think maybe I'll give that as an assignment. You have one already. This course is about assignment. And you signed up. So now there's nothing you can do. Yes. Yes. So go back and rerun the theta.
Yes.
You did it.
Yes.
And so when we are testing it, I changed mine to 5 now. So I'll do this, the next one. You see 100. I do the next one, I do the next one, I do the next one. You, okay.
I'm saying, initially when we tried the 0.02,
2, yes.
when they didn't work,
Yes.
I've gone back to the same one, but now it looks like
It works.
I only changed the upper and the lower. Brought it down.
You brought it down.
Yes.
Okay, so the idea is also that, you see, the way maximum likelihood works is that it iterates to the solution.
Okay.
So if because we know that the solution is close to 0,
Mm-hmm.
if I give it a wider range, it means it's like maybe you are going to Kumasi. Somebody start at the Joso and then you are starting in Accra.
Mm-hmm.
You are searching for something. Because the person is closer to Kumasi, will reach there and get it. So that's the sort of thing that happens.
Okay.
So the closer it is to the solution, the faster it will get to it.
Okay.
Yeah, that's why I said that's the defect or the difficulty with maximum likelihood. We don't know what we want to find. But it says, give me something close to it so that I can work towards it.
Mm-hmm.
Yeah. So I won't be surprised if it works. Sometimes it depends. The estimator may depend on the size of the unknown population parameter. And so maybe if it is, that's why I came back to check what they did. But unfortunately, they did not compare the estimators. They only gave theta is this, and then the bias. Okay. So it could also be that, okay, I did not read. Maybe I have to read. The first one maybe. It's a long time. Okay, so table 1 shows that the bias and MSC decreases so and so. In terms of bias and MSC, the S gamma shows more flexibility compared to the exponential distribution. I think the exponential is in table 1 for each selected theta. The score related to okay, so they only work with exponential and S gamma. But what I want us to do is to be able to compare maximum likelihood and what? The moment estimator, which does best. In this case, because we know the value, we can do it several times and find the bias and find the MSE, and then we can conclude on which one is the best. Is everybody okay with this? Okay. Yeah, so yeah. Today I promise that I'll give you some time. I don't want to break my promise. So you are thanking me, I haven't finished. Okay, so let's see. I changed it to 5. Moment estimator gave me 6.1. This one, MLE gave me 6.07. So you see, the MLE is a bit closer to the 5 than the moment. And we can do this and increase the sample size and see what really is happening, and so forth.
So, Prof, the last question.
Yes.
What should guide us when we are indicating the lower and the upper?
That's what I said. In a simulation, you know, so it's easy. Okay. It is when we have a data set, then it becomes a problem. Because if it's a data set, for example, claims, we don't know theta. So how do I provide minimum and maximum? But usually you have the range of values of a parameter. In this case, the parameter is positive. So you can choose 0 and infinity, but you give MLE more work to do because it has to search within a wide range to find it. Yeah, that's it. Okay, any question on this? Okay, so what I want you to do is that I think yesterday the assignment you were to find your own data, right?
Yes.
Good. So now we have done this S gamma. The data that you find, please fit the S gamma distribution to it and superimpose the distribution. We've already found the density, isn't it? So if you have the data and you pass it through the S gamma distribution, it will find the densities for you. What do you have to do? Arrange the data in order. It must go with its density, and then you superimpose it on it as well. So that's it. And that should be the end of our tutorial today. Okay. How many weeks do we have now? 3 more weeks.
Yes.
So we've done only 3 weeks.
Yes.
Hey, and you have... Okay, then we are on course.
Okay.
Yeah. We've